We've been exploring the construction of the real numbers. And wait, let me pause this for a second. Right. So there's a few things we have to mention about the real numbers. Everything about the algebra of the real numbers has been mostly covered, and you have all the tools necessary to prove that these form a field. Right? I even showed you how to find inverses in terms of Cauchy sequences of the rationals. That was the last major result we saw the last time. But again, the same with the rationals. What about the order? How do you order the real numbers such that you don't just get a field, but an ordered field, right? That's a natural question. So recall that a Cauchy sequence of rationals is positive if eventually all the terms are positive. All of these sequences, by being Cauchy, the only thing that matters about this sequence is what happens eventually at infinity, so to say. It's completely irrelevant what happens in an initial segment. For the first 1,000 terms of a sequence, they don't give you any information because they could change and still give you an equivalent Cauchy sequence. I've mentioned this in the last lecture as well. Every real number has infinitely many Cauchy sequences that represent it. And the reason why that happens is because you can change everything about the first few terms, but that doesn't change the important properties of the sequences. For example, the fact that they're bounded, the fact that if they converge to a certain number, then that number doesn't depend on the first few elements, right? And similarly, being positive or negative shouldn't depend on the first few terms. So for some large number n, eventually, after that big number n, all of these are positive, or let's say is positive. Positive rational, which I definitely defined. Right, then how do you define the difference between two sequences? We write if x and y are real numbers, then we say x is less than y. If what you do is you pick a representative, right? You pick a sequence that represents x, and you pick a sequence that represents y. And whatever sequence represents y, you write that, and then minus xn is positive. Right, so Cauchy sequence xn I should add. Right, in other words, when are two real numbers, how do you compare two real numbers? So this is the idea. Here you have a real number x, and here you have a real number y. Is y the one that's bigger? Yeah. Right, and here are the sequences that approach those numbers. So maybe I can write them on the right side. Maybe that makes it a bit more clear, right? So this is y, and this is x. The subscript is the index. So someone asked in the chat, the subscript is the index, right? So I defined this in a previous lecture. This symbol basically means that this is a sequence, right? It's a function from the naturals to the rationals. So this represents the number y0, y1, y2, y3, and so on. And this is the sequence. But instead of writing this out and then having the three dots, I find it more comfortable to just use a subscript n, where n is the index, right? But I could use any index. I could use k, I could use m, I could use q, anything I want, right? And actually, this helps me with the example already. Yeah, you're welcome. So let's say this is y0, this is y1. Maybe I can move these around a little bit to add some variety, right? Like I said, what happens at first doesn't matter. The only thing that ever matters with a Cauchy sequence is what happens eventually. So I'm going to connect these with a line just so that you can easily tell the direction that the sequence is going. That's just a representation thing, right? They're not really connected by a line. They're just points. They're just dots, right? Y5. And the idea is that eventually they will approach Y because that's what Cauchy sequences do. That's how I defined the real number Y. It's, in a way, it's the limit of the sequence. Of course, I haven't defined a limit yet, but this is exactly what that is. Now, the same thing happens with X, but X could have a very wild behavior, right? It could jump above the other line, X1, X2. It could be extremely erratic, X3, then maybe this is X4. The point is that eventually they have to get closer and closer and closer, these points between each other, because it's a Cauchy sequence, right? So what does it mean for y to be bigger or equal, in this case bigger, strictly bigger than x, right? Actually, I forgot to include the possibility of them being equal. It does say bigger or equal, right? But if it's positive, it means it's strictly bigger. So let me clarify that. So what does it mean for y to be bigger than x? It means that even if the sequences don't always satisfy this, eventually they do. And this eventually, in this case, in this example, happens when n is 5. If you look at this after n is 5, then they don't cross ever again. They don't cross anymore. And they can't cross because if they crossed everywhere, like if they crossed after every threshold that you pick, then if you think about this, then being Cauchy sequences means that they have to be the same number, right? So this is how you define the order of the real numbers. Now, there's something else that we can do. So if we are already familiar with the real numbers, these Cauchy sequences are just sequences of rationals that are approaching the real numbers, right? So let me give you a more concrete example. So now that we have constructed R, we can think of these classes in the following way. So let me give you a very simple example and you'll see how this makes perfect sense. The number pi is a real number, right? And if you study the number pi, you'll know that it has this weird representation. Actually, I don't know. I used to know many of these digits by memory. I forgot what comes after 2. What is it? 6, 5? Anyway, so it goes on forever and there's no repetition. And some people conjecture that every finite sequence of numbers will be found here somewhere, right? So this will contain symphonies and novels and pretty much anything you want. Any question to any, the answer to any question about the universe you may have, you can encrypt it into a number and you might be able to find it there. It's a conjecture. No one knows if that's true. There are other real numbers for which that is true, but maybe I can give you an example of that later. This is just something you may have read somewhere. It used to be quite popular. People shared this on social media. Like, did you know that if you take the number pi, then you can find the Beethoven's 10th symphony, which he never wrote, encoded into its digits? And it's like, yeah, we don't know. No one knows that's if that's true. That will be true for other real numbers. And like I said, if you're interested, I can give you a very simple example. It's so simple that it actually makes pi uninteresting in this regard. Anyway, I'm getting off topic. So this is a real number. How would you represent pi? There's more than one way. I just mentioned there's infinitely many ways of doing this, but sorry, that doesn't make sense. So pi is a real number. It means it's an equivalence class. And let me add maybe call it Q this time so that it's more explicit that these are rationals, right? So pi is this. That's how I define the real numbers. Every real number is a class of a Cauchy sequence. So where Qn is Cauchy, a Cauchy sequence rationals in rationals, right? So that's how what the definition is, but maybe we can pick a canonical example of such a sequence, right? There's many of them, but there's one that will be much more natural than the others. And this is how you do it. And then you'll see why this is way more intuitive than it might seem at first. We have to do this abstract stuff first so that we can properly construct the reals. But now that we did all this abstract nonsense, then we can make our lives simpler by picking things that are just easier to work with. So the first is a number 3. This isn't, I mean, it's an integer, of course, but of course, I'm thinking of this as a rational, right? Q1 would be 3.1 because 3.1 is just 31 divided by 10. So this is obviously a rational, right? Maybe I don't have to write this every single time. Well, what about Q2? Q2 could be something like 3.14, which is 300 and I mean, I'm not saying that this is the simplest way of writing these. It's not reduced, right? I don't know if these numbers are co-prime. Actually, they aren't. They're both even. But I don't care. There's no reason for me to go through the trouble of reducing that fraction. 3.141, right? Maybe, hopefully you can see where I'm going with this. This is the number 3,141 divided by 1,000, which is obviously rational. And you can go on forever. So if you think about it, this is what we're actually doing. All we're doing is rationals have a periodic or just finite representation as decimal numbers because they will always look like this. It's always a fraction. It must terminate and then repeat, or just terminate and then be all zeros or something like that. So all the real numbers are, in terms of these representations, is we allow these decimal fractions to be whatever we want, right? These decimal, sorry, not fractions, these decimal representations can be anything. It can be any sequence of integers that you want will represent a real number. And I just told you how to find that real number, right? It's the class of this Cauchy sequence. You can easily see why this is a Cauchy sequence, right? They get closer and closer because every step gets you within 1/10 of the previous number, and then 100th, and then 1,000. So the distance between these numbers shrink, right? So they get closer and closer and closer together, and indeed they approach pi. Like I said, this is not the only sequence of rationals that approaches pi, but I think I just convinced you why this sequence in particular is the most natural one, right? This is the one we should pick in the context of decimal notation. Okay, so there's one thing that I haven't mentioned yet, which is by far the most important property about the real numbers. So let me write this as a theorem. So why did we bother doing this? This is by far the most complicated construction we have seen so far in the course, right? We started with the naturals and we constructed the integers. Okay, that wasn't too bad, but if you look at problem number 2 in the problem set, then you can already tell that there's some non-trivial thing going on there. Then we constructed the rationals, and there's a similar thing that we can talk about later, analogous to problem number 2. Then we constructed the reals, and it seems like it's so much harder, right? Because here we have infinitely many representatives that are scattered, or it's a lot more chaotic. There's a lot more freedom, and it becomes more abstract if you do it that way. So why did we bother doing that? What makes the real so special? The rationals are already a field. Anything we could have solved with the rationals, we can solve here too. So, well, and the other way around. So the thing that makes the real special is the following property. So every non-empty set, non-empty bounded, let's say with an upper bound. Yeah. Every non-empty set of reals with an upper bound. The same thing works with lower bound, of course. It's analogous and actually follows from this result with upper bound. has a least upper bound. And what this means is that the real numbers don't have any holes. Every time you take a sequence that seems to approach something, it indeed it approaches something inside the real numbers, right? And this follows almost from the definition, right? Every real number is represented by a Cauchy sequence. So if you have a Cauchy sequence of these things, they in fact have a limit, which is the real number that you started with. Now, this theorem isn't trivial. I'm not saying that it just follows from the definition or from the construction, but it is very important. So maybe let's spend some minutes thinking about why this should be true. Actually, not a short proof either, now that I think about it. So before I start with this, are there any questions about anything I've mentioned so far? Is this example with pi, does it help clarify what is going on in a way? You can always pick a sequence that makes things easier, right? There's so many sequences you could have picked, but why wouldn't you pick this one where the decimal notation tells you exactly where it is you're going? I will stop this for just 1 minute in case you have questions. Yes, exactly. So the thing about maybe I think it might be worth so someone is asking, so the real numbers are composed of Cauchy sequence of rationals. So maybe just for the sake of maximizing benefit, let us focus on the intuition for this theorem, right? This theorem is kind of technical. I think you'll benefit more if I focus on the intuitive part. Also, you don't need this theorem, right? Right now. Okay, so what is the idea? Now, I mentioned that between any two rationals, 0 and 1, there's infinitely many rationals, right? There's 1/2, there's 1/4, there's 1/3, and all of these, the dense set. But there's still a lot of things that are missing. And the easiest example of this, sorry, let me make a better example of this. The easiest example is if you focus on something like square root of 2. The square root of 2, we proved that it doesn't exist in the rationals. There's no rational number that you can square and get 2. So the square root of 2 is not a rational. It means like there's like a hole, right? It doesn't belong there. But we can get arbitrarily close to the square root of 2 by picking a sequence, right? So the set that I mentioned earlier, you take all rationals whose square is bigger than 2, right? Let's say smaller than 2, same thing. All rationals whose square is smaller than 2, then what is this doing? Well, you can pick a number that satisfies this, like 0, right? 0 squared is smaller than 2, so is 1, right? But then 2 is already bigger, so 2 is not here. 2 will be on the right side. But my point is, if you start writing out fractions, then you can pick closer and closer and closer and closer points that approach this whole. You can never get to the whole because it's not a rational. It's not there. There's no rational satisfying this, right? So this set is bounded, but in the rationals at least, has no least. Sorry, I think I went the wrong way. Has no greatest lower bound. Right? There's a lot of lower bounds for this. Sorry, upper bounds. Upper bound, upper bound. Least upper bound. Because such a number would be the square root of 2, right? It's at the threshold. It's the smallest possibility. Okay. Still think I'm changing up these things. Maybe it should be bigger in that case. Right. So just to finish the idea, least, I think I meant greatest here. Okay, this doesn't matter. The point is that there's a hole in the number line, right? So this produces this hole. How do you fill that hole? Well, you have to figure out a way to talk about that hole without talking about the square root of 2. We can do that for this set in particular, but there's many other sets that don't even have a representation. How do you represent pi as a set? That's not obvious at all, right? There's no easy way of doing that. So the way you do that is Cauchy sequences, because Cauchy sequences always approach these holes even if they're not part of the rationals. So when you're taking the quotient with the equivalence relation, what you're actually saying is you pick a representative, and that thing that you're picking is a whole. That's the whole that you're now talking about, right? And I already told you that constant sequences represent the rationals inside the reals. Sorry, let me answer the chat. So we use this fact to prove commutative and associative laws of real numbers. Yes, that is correct. So once you have Cauchy sequences, you define a way to multiply them and to add them, which I did in the previous lecture. And that just depends on the way that we're adding and multiplying rationals, because in the end, you're doing something term-wise, and every term is just a rational, right? Now, I should point out this is not the only way of constructing the real numbers. There are other ways that are vastly different. If you're interested, then you can look at this up. So there are other ways of constructing the real numbers. For example, and this is actually a method that I prefer, but it makes the algebra really difficult. The algebra that we have here is easy. It's just how do you add two Cauchy sequences? Well, just term-wise, coordinate-wise, right? One after the other. Same thing with multiplication. It's harder to prove that this theorem is true, right? But there's another way of constructing R that makes this theorem easy, but the algebra hard. But like I said, we're focusing more on the algebra because that's usually more useful. And if you're curious about this, you can look up the concept of a Dedekind cut. It's very intuitively it's the same thing, right? You need to figure out a way to talk about the holes without talking about that which will fill the hole after you constructed the reals. So this is why this construction might seem a bit abstract. But yeah. So this theorem, by the way, this property is called completeness. And the only difference between the rationals and the reals in terms of this construction is that this gives you a complete structure. It has no holes. It's complete in that it has no gaps. You can find the thing filling every single possible gap. So every Cauchy sequence in the real numbers actually does converge to a concrete specific point on the number line, which doesn't happen for the rationals, and I just gave you an example, right? Are there any questions about this? Let me pause this for a second. The second problem in your problem set has a very interesting question. It says that if, so this is the problem set 3 question or problem 2 says that what can you say? We've talked so much about the algebra, so what can you say? What can you say about this as an order structure? Because we talked so much about the algebra, right? And we could also do this question in terms of algebra, but let's just focus on the order. What can you say about this? This is different from other orders, right? So for example, one property is that the order is linear. And linear, I defined more than once in the past. It means that you can compare any two elements, right? They're on a line. Another thing that you can say, it is unbounded. It has no maximum and no minimum element. And another thing that you can say about the integers is that they're kind of discrete, right? They're not close together. They're the opposite of dense. You can always find between any 2 points only finitely many others. That's the opposite of being dense, right? They are isolated. They are kind of far apart. There's a lot of space between the integers. Between that's not how you spell between two integers, between two elements, let's say. There are finitely many, right? In the rationals, this is always infinite. But with the integers, it is always finite. Between any two elements, there's only finite. Even if you pick minus 1 million and plus 1 trillion, well, there's only finitely many elements in between. Finitely includes zero, by the way. Between 0 and 1, there's nothing, right? There's 0 elements. Now, here's something interesting. Whenever you start writing out properties of an object, like I just did now, this list cannot go on forever. I could make up stuff, right? I could say, well, between, let's say, what else? What else could I be saying about this? Between consecutive elements, there's nothing or stuff like that, right? Okay, I won't even bother writing that down. My point is, this list will not go on forever until there are things that follow from the first few properties. And what I claim with the integers is that any other property of the integers follows from these three. So I could have defined the integers as a linear order that is unbounded and has property number 3. And that tells you everything there is to know about the integers. Because any other structure satisfying these three things is the same as the integers, up to a relabeling of the elements, right? It's isomorphic to the integers, and that is what you're asked with proving in question 2. Question 2 is a bonus question, so you don't have to do it, but I recommend you do think about this for a little bit. Now, something that I haven't filled out the details yet, but I can do that if you're interested. In the additional problems, the ones that aren't even marked, you have to come up with the same thing for the rationals, right? What can you say about the rationals? Well, it's linear. It's also unbounded. It cannot satisfy property 3 because then it would be the integers. It would be the same. It would be equivalent to the integers, which it is not. So actually, it satisfies kind of like the opposite, right? It is dense. Now, there's one more property that is important that doesn't follow from these three. Can anyone tell me what other important difference as sets can you find between the real numbers and the rational numbers? And I have mentioned this at some point in the past. So what other property do you think makes the rationals unique in the sense that every other property about the rationals as an order will follow from these three things? There's a fourth thing here. And you can also ask yourself the question for the real numbers, right? So the real numbers, well, they're also linear. They're also dense, but it's not really that important. They're also, sorry, let's maybe keep some order here. Unbounded. Maybe I can write dense, but there's something else going on here that's more important. So what distinguishes these two structures or these three structures? What makes them different in a very abstract level if you didn't know anything about these structures? This by the way, this thing where I keep writing out properties until everything follows from the ones I have so far is called characterizing. I am characterizing the integers as a linear order because I'm writing out properties that uniquely identify the rationals as an ordered, or the integers or the reals as an ordered structure. So I will maybe give you a few minutes, and with some imagination, you can think about what makes these structures so different from each other. They have a lot in common, right? They're unbounded, linear, whatever, but there's things that are very different. So who can mention any property that comes to mind about the order? I'm not talking about algebra right now. That's an entirely different subject. We could do the same for the algebra as well, right? But in terms of order, what makes this interesting? So we don't have to answer this now. This is a slightly off topic. This is not part of the subject. And like I said, it's only in the additional exercises. But if you go to the feedback form where you pick a subject, this is one of the potential things that we could discuss in a lot more detail in the last chapter. This is part of, I think, set theory this would qualify as set theory. So if you're interested in these sorts of questions, and there are some really difficult problems that have to do with these things that no one has quite figured out in a way, right? Then we can talk about that. So I will once again share the feedback form with you in case you haven't filled it out, although I think no one has joined the meeting since then. Let me just show you the feedback form one more time.